Hello and welcome to the presentation of Team Proto's Intel server robot. My name is Chad Campbell and I am the team manager for the project. I also participated in the design, analysis, manufacturing, and assembly of the overall system. Chris?
I'm Chris Merrikin and I helped design and analyze a lot of the parts, as well as I tracked the budget and the ordering of parts providers.
I'm Arif Islam, so I'm the team secretary, and I also worked in the electromechanical machines and programming.
So the idea for the project is rooted in the growth of the data warehouse market. As the data warehouse market grows in number and size, a degree of automation is required to maintain all of the hardware. Based on the projected net worth of both the data center and industrial automation markets, we decided it would be worthwhile to design and build a robot capable of transporting servers in a warehouse setting.
The project was designed and prototyped over the course of 2 semesters. The entire first semester was conducted remotely from our homes because of COVID-19 restrictions. And we accomplished this by using video chat, email, text messaging, and cloud-based platforms like Google Drive, GradCab, and GitHub. The first semester, we focused on project selection, concept generation, design, and analysis. As a team, we selected a design proposal from Intel to build a server maintenance robot and generated the concept based on industry needs, feasibility, and finances available to us. Our design was based on selecting simple mechanical and electromechanical processes that were practical and effective in their operation, simple to manufacture, and kept our costs low. We used computer-based analysis and design software, as well as paper calculations to select the material types, dimensions, and safety factors. The second semester was focused entirely on producing a functional prototype that would serve as a proof of concept. To do this, we had to make some redesigns based on available materials, machining capabilities, and our budget. We spent a lot of the semester in the shop manufacturing parts and assembling the robot because we had to ensure the mechanical and electrical components interfaced and operated according to our designs. We also put a lot of hours into motor control, wiring, computer and network integration, and powering the overall system. We spent the final days of the project doing system-level operation, testing, debugging code, and documenting the entire project. To make sure that we would be able to accomplish all of our goals, we created a comprehensive timeline that enabled us to stay on task and on schedule. This helped us remain vigilant and aware of our time constraints to make sure that we would arrive at the end of the project with a functioning prototype and having met all of the course reporting and participation requirements. This is the timeline we followed for the first semester. This is the timeline for the first half of the second semester. And this is the timeline for the second half of the second semester leading up to the completion of the project.
Using Autodesk Inventor and our online collaboration tools during Senior Design 1, we designed a robot which can be broken down into 5 main systems under 2 categories: mechanical and electrical systems. Mechanical systems are the chassis, which supports the entire structure, the server bay, which holds the retrieval unit once it's designed, the mobility, which relies on 4 NEMA 34s with differential steering, and then the lift, which is based on 2 NEMA 23s with a gear reduction for linear actuation.
Here we used ROS, which is a robot operating system, on a Raspberry Pi to design our robotics system. The whole thing is programmed in Python language. And in terms of like electromechanical stuff, such as the NEMA 34 and NEMA 23 motors, we have selected right motor drivers, which you can see on the bottom center picture. There's the NEMA 34 driver, 7.2 amps. And the right is a NEMA 23 driver, which is 4.2 amps. On the left, you can see our sensor that activates within 10 centimeter of reach and stops the robot.
So a few different design tools were used to analyze the design. In all of them, a minimum safety factor of 2 was used because the robot operates in a very predictable environment with low impact actuation. In brief, here are the methods we used to analyze the design and ensure the safety factor was met or exceeded. For parts like the motor shafts, fasteners, and machined items, hand calculations and stress transformations were used. For the gear reduction in the lift system, the bending and contact stresses in the gears were analyzed. For the chassis and lift system, FEA simulations were run, and then finally, Simulink was used to analyze the step response of the electrical components.
As an engineer, we believe that the first thing is to ensure the safety, and that's why we made sure that all the codes, we complied all the codes. So as you can see on the right bottom box, we have listed all the codes that we use to design our prototype so that it ensures all the safety features that was required by the customer. And on the left box, you can see the physical specification of our prototype. We have listed the footprint, wheelbase, the programming language we use, and all other stuff listed there.
Now you might have noticed that the cost to build the project was over $3,000, which is way over our budget. However, as the chart here shows, we were able to cut costs dramatically, allowing us to demonstrate capabilities of the design. The first prototype idea was a simple demonstration of each of the systems, basically one half of the robot, and you can see that in the upper right-hand screen. By using available materials from the machine shop, we recycled them, and we were able to update the prototype to include nearly the entire robot. You'll get to see a picture of this and a demonstration of it here soon.
While we were building our prototype, we had to make some changes due to lack of funding, and we also found some recyclable parts which are not really same as our actual design. So the first thing we modified was our gear train for the lifting device. As you can see on the bottom left picture, the CAD model of our actual gear train, but we changed that to the right one that is on the slide. And we also made some modification to our chassis due to the recycled parts.
The majority of the prototype components were machined at St. Martin's Manufacturing Lab using the lathe, mill, and drill press machines. We also use a lot of manual and hand power tools along with supplies and testing equipment from the mechatronics, fluids, and computer labs to put together and test our prototype. The majority of the assembling, programming, electronics testing, and wiring took place in the senior design lab at our workstation. Almost all of the structural components are made out of aluminum and put together with steel fasteners. The chassis was initially meant to be welded together, but circumstances forced us to devise a way to assemble the chassis using nut and bolt fasteners, which actually ended up working out well for us from a prototyping point of view. The control system evolved over the course of the entire project and was an ongoing process to adjust and debug throughout the design and prototyping processes. We initially used an Arduino controller to run our robot, but ran into problems when trying to run multiple processes at the same time. So we switched to a Raspberry Pi 4 computer running ROS to control our system, which worked out very well for us.
This is where we tested our prototype, and as you can see, the testing had 4 major requirements: this moving capability, lifting, distance sensor, and the remote operation. So as you can see on the bottom right, the terminal shows the distance data that is from our sensor. So the sensor is activated when there's something within 10 centimeters of the robot. And we have also included the robot to our Wi-Fi, and as you can see, it can be operated from a remote computer.
While we accomplished a lot in the course of this project, there's still a lot of room for improvement. Part of the deficiencies are due to decisions made based on budgetary constraints. So with more funding, another group could really take this machine to the next level. Some of the areas of improvement are the mobility, the lifting capacity, and to navigation and sensors. For example, the NEMA 34s are right at the brink of their capabilities, to the point that the robot struggles to turn while it's driving on the ground. So a higher torque motor or a gear reduction could improve this. The lift system was also designed to be pushing the limits of its capabilities due to the cost of gearing. The original design had a gear ratio of about 118:1, and this prototype has a gear ratio of 4:1. That being said, to add more tiers and lifting capacity, the gear reduction will need to be upgraded. Finally, the navigation of the robot is completely based on human input at this point. Ideally, in the future, it would have a high degree of autonomy.
That brings us to the conclusion of our presentation. We'd like to thank everyone watching and send out a special thanks to our sponsor, Trestle, for providing materials to our project. As a team, we hope that the work we've done will serve as a basis for future work in automated servo retrieval systems and general robotics development. For more information on this project, build videos, demonstration videos, and operating videos, you can visit our website on GitHub or our YouTube channel at the links below, or follow the link on the screen. If you have any other inquiries, you can also contact the design team directly at the provided email addresses. Thank you for watching.
Thanks.
Thank you.